Have you ever been deep into coding a C++ application, feeling pretty good about your logic, and then bam, you hit this mysterious, really frustrating performance bottleneck?
Uh-huh.
Maybe it's a game, micro-stuttering right when you're about to land the winning shot,
Uh,
or maybe a high-speed system missing a critical market opportunity just by milliseconds.
yeah, that sounds familiar.
You've checked your algorithms, your logic seems solid, but the actual culprit is, well, it's hidden.
Somewhere deep.
Exactly. So today, we're going on a deep dive into that exact mystery. We're unpacking the crucial, often kind of overlooked world of C++ memory allocators.
Right. The things that give you memory when you ask for it.
Yeah, and our mission today is pretty clear. Figure out why the default ways of getting memory can sometimes uh, really hamstring your performance. Then explore some powerful alternatives and, crucially, learn when to actually use them to unlock your application's speed.
Sounds like a plan. It's a really important topic.
Okay, so let's talk about that glitch in the matrix. You're in a game, it's smooth, and this tiny, infuriating freeze. Or that trading system just misses, feels like a bug, right?
Totally. Your first instinct is always, what did I break in the logic?
Exactly.
Yeah.
But what if the problem isn't your brilliant game logic or your fancy trading algorithm, but just how your program asks the computer for memory? Is there really a hidden cost to something as basic as new and delete?
It's a great question because, yeah, for decades, C++ developers have just relied on new and delete. They're the workhorses for dynamic memory, from the heap.
This seems simple enough. Ask for memory, get memory.
On the surface, yes. But what's fascinating and kind of the core issue here is that they hide this really complex dance with the operating system behind the scenes. And that dance, well, it often carries a pretty significant unseen cost. It's rarely free.
Okay, that makes sense for using new and delete directly. But what about, say, our standard library containers, things like std.vector or std.list? Are they somehow getting around this dance, or are they maybe falling into the same traps?
Ah, good point. Unfortunately, no, they're not exempt. Even something like std.vector doesn't usually call new or delete directly. It uses something called std.allocator.
Okay.
And by default, std.allocator is basically just a thin wrapper. It just forwards those requests straight to the global new and delete operators.
So you're inheriting all those hidden costs anyway.
Pretty much, yeah. But it's this allocator model itself that provides a really critical distinction. It separates memory allocation, which is just getting the raw, uninitialized space, from object construction, which is actually calling the constructor to make it a live object.
Oh, interesting. So you're saying when I write new my object, I'm doing both things at once, allocation and construction.
Right.
But with allocators, I can pull those two steps apart, like std.vector.reserve just gets the raw memory.
Exactly. It allocates raw space.
And then pushback actually constructs the objects in that pre-allocated space. That separation sounds powerful.
It is. It's a fundamental concept. And yeah, the convenience of the default allocator, where you just say new and it magically works. It absolutely comes at a hidden cost we don't often think about.
So let's get into it. What are these hidden costs? If new and delete aren't just simple function calls, what's really happening under the hood that can, cripple performance?
Well, the main problems, I'd say, fall into about three critical categories. First, there's system call overhead and context switching.
Okay.
Your application runs in what's called user mode, right? It's kind of a restricted environment. To do anything significant with system resources, like asking the OS for more memory pages, your program has to make a system call. It has to ask the operating system's kernel mode to do the work.
And that's not like just calling another function in my code.
Not at all. It's much heavier. This context switch means the CPU literally has to save the entire state of your running application, all its registers, its current instruction pointer, everything. Then it switches over to the OS kernel. The kernel does the memory management work, figures out where to get memory from, updates its tables, and then it has to switch back, restoring your application's entire state so it can continue.
That sounds incredibly expensive for just asking for a little bit of memory.
It is. We're talking hundreds of nanoseconds, maybe even microseconds, just for that switch back and forth. Think of it like a factory worker needing a single screw. Instead of grabbing it from a bin, they have to stop the entire assembly line.
Uh-oh.
Walk over to the manager's office, fill out a form, wait for approval, get the screw, walk back, and then restart the whole line.
Ouch. And if your program is doing that thousands of times for lots of small allocations.
That's death by 1,000 cuts, exactly. Performance just bleeds away.
Okay, so system calls are bad. What's next?
Well, this leads nicely into the second major issue, Memory fragmentation.
Ah, the Swiss cheese problem.
Yes. Precisely. Imagine your computer's heap memory starts as this nice solid block of chocolate. As your program runs, it allocates memory blocks of different sizes, then frees some of them. It's like taking bites out of the chocolate bar, maybe putting some crumbs back in different places.
Right.
Over time, that nice solid block gets riddled with holes, small, unusable gaps between the allocated chunks. So even if you technically have plenty of total free memory added up, you might not have a single contiguous hole big enough to satisfy a request for a larger block.
And that can lead to std.battlelock. Your program crashes even though top or task manager says there's RAM available.
Exactly. It's especially common in long-running applications like game servers or, financial systems that run for days or weeks. I actually remember debugging this one server application once. Performance would just inexplicably tank after about 36 hours. Yeah, it took ages to figure out. Turned out it was just a slowly growing, fragmented heap. Eventually, even relatively small allocations were struggling to find space, all while the system monitor showed plenty of free RAM overall. It was a real head-scratcher until we actually looked inside the memory layout.
Wow, that's insidious. Okay, so the problem isn't just getting memory, but also where it is and how it's arranged, which I guess brings us to the third big one, the tyranny of the cache and data locality. This sounds like where things get really interesting for raw speed.
Oh, absolutely. This is often the biggest factor. See, modern CPUs are just orders of magnitude faster than main memory than RAM. It's a massive speed gap.
Like ridiculously fast.
Ridiculously. To bridge this gap, CPUs rely on these tiny, super fast memory banks right on the chip called caches, L1, L2, maybe L3 cache.
Yeah.
Think of it like this. Accessing data that's already in a CPU register is like picking up a tool you're already holding in your hand. Instant.
Yeah.
Accessing it from the L1 cache is like grabbing it off your tool belt. Super fast. L2, L3, maybe the workbench right next to you. Still really quick.
But main memory.
Accessing data from main RAM, that's like having to stop work, walk across town to a warehouse, find the tool on a shelf somewhere, and walk all the way back.
Yeah.
It takes ages in CPU terms.
So when the CPU needs data, it checks the caches first. If it's there, a cache hit, boom, super fast.
Exactly.
But if it's not there, cache miss, the CPU just stalls. It sits there doing nothing, waiting for that slow trip to main memory.
Precisely. Hundreds of clock cycles just wasted, waiting. That's a huge performance killer.
Okay, so how does the allocator tie into this?
Well, caches work effectively because of a principle called locality of reference. There are two types. Temporal locality means if you just use some data, you'll probably use it again soon. Caches keep recently used stuff around.
Makes sense.
But even more critical for allocators is spatial locality. This means if you access one particular memory location, you're statistically very likely to access memory locations right next to it soon after.
Like iterating through an array.
Exactly like iterating an array. Modern hardware is built for this. It doesn't fetch memory one byte at a time from RAM. It fetches it in chunks called cache lines, typically 64 bytes. So if you access byte number 5, the hardware says, okay, I'll just bring bytes 0 through 63 into the cache while I'm at it.
Because it assumes you'll probably need the neighbors soon.
Right. So data structures that keep related elements close together in memory are incredibly cache-friendly. They get lots of cache hits. This is the counterintuitive bit. For modern CPUs, memory isn't just memory. It's really about proximity. And often, the single biggest performance killer in C++ isn't your algorithm's theoretical big O complexity.
It's how badly it treats the cache.
Exactly. How brutally it destroys spatial locality. And this is where std.list often falls down hard.
Wait, std.list, I always thought that was okay for, like, constant time insertions and deletions if you have an iterator.
It does have O1 insertion deletion if you already have the iterator pointing to the right spot, but its Achilles heel is cache performance. Think about how it works.
Okay, nodes allocated separately.
Right. Each node containing the data and pointers to the next previous node is allocated individually using new, via the default allocator, probably. So those nodes end up scattered randomly all over the heap memory.
I see where this is going.
So when you iterate through std.list, you're basically pointer chasing. You jump from one random memory location to another completely different, faraway location than another. What does that mean for the cache?
Cache miss. Cache miss. Cache miss. Probably for every single element.
Almost certainly. Whereas std.vector, because it stores its elements in one big contiguous block,
Is super cache friendly.
yeah,
Iterating it is mostly cache hits once the first cache line is loaded.
exactly. Orders of magnitude faster in practice for iteration, even if the algorithmic complexity looks similar on paper. And the default allocator, being general purpose, is completely oblivious to these access patterns. It often actively works against spatial locality by scattering your data.
That's a really powerful distinction. So, okay, this paints a pretty clear picture. The default way is convenient, but it can cost us dearly in system calls, fragmentation, and especially cache performance. What does this mean for us, the developers? It sounds like we need to take control back from the default allocator.
Absolutely. That's the key takeaway. We need to take control.
What's the guiding principle here? How do we approach these high-performance solutions?
The fundamental idea is to shift your thinking. Move away from reactive, per-object allocation, asking the OS for little bits all the time, and towards proactive bulk management.
Proactive management.
Yeah. Instead of constantly pestering the OS, you make one, or maybe just a few, large allocation requests up front. You get a big chunk of memory, sometimes called an arena or a region.
Okay, grab a big slab of memory first.
Right. And then you manage all your smaller actual object allocations internally within that pre-allocated arena. You become your own mini memory manager for that chunk.
And the benefits.
Huge. First, you drastically reduce those expensive system calls. You might make one call at the start instead of thousands. Second, you contain fragmentation. Any fragmentation happens inside your arena, not polluting the global heap. And third, crucially, you often get a nice contiguous block of memory, which is fantastic for that spatial locality and cache performance we just talked about.
Okay, that makes a lot of sense.
Yeah.
So what's the simplest way to do this? The fastest, maybe? I think I've heard of something called a linear allocator or an arena allocator.
That's right. The linear allocator, sometimes called a bump allocator or arena allocator, is incredibly simple and often the absolute fastest for specific scenarios.
How does that work?
You get that big block of memory, your arena. The allocator just keeps a single pointer, let's call it the bump pointer, that initially points to the very beginning of the arena.
Okay.
When you ask for, say, 16 bytes of memory, the allocator simply returns the current address pointed to by the bump pointer.
Here you go.
And then it bumps that pointer forward by 16 bytes. The next allocation starts from there.
So allocation is just moving a pointer.
Yep. Just simple pointer arithmetic. It's incredibly fast, 0-1 constant time. Doesn't matter how much memory you've already allocated, the next allocation takes the same tiny amount of time.
Wow. What's the catch? Sounds too good to be true.
The catch is deallocation. You typically cannot deallocate individual objects allocated this way.
Ah, so you can't just free up that 16 bytes you allocated earlier.
Nope. The only way to free memory in a simple linear allocator is to free everything allocated from the arena all at once. You do that by simply resetting the bump pointer back to the beginning of the arena. Poof, all gone.
Okay, so it's perfect for things that all have the same lifetime, like temporary data you only need for a short time.
Exactly. It's ideal for short-lived, temporary data where everything can be discarded together. Think calculations within a single function or, as we'll see, data needed just for one frame in a game.
Right, okay. Linear allocator, super fast allocation, bulk deallocation only.
Yeah.
But what if you do need to allocate and deallocate individual objects frequently, and you still want to avoid hitting the OS all the time? Are we stuck then?
Not at all. That's where a different strategy comes in, often called a pool allocator.
Oh, pool allocator, okay.
This one is specifically designed for allocating and deallocating many objects of the same fixed size very quickly.
Same size. That's the key constraint.
That's the main one, yes. The pool allocator starts with its own arena, but it pre-divides that entire arena into equal-sized chunks, the size of the object you want to allocate.
Okay, like a grid or a stack of identical boxes.
Exactly. And it maintains a free list, which is basically a linked list of all the chunks that are currently not in use.
Right.
When you ask for an object of that specific size, the allocator just takes the first chunk off the free list and gives it to you. A one operation just pop from a list.
Super fast again.
Mhm.
And deallocation.
Also a one. When you're done with the object, you just give the chunk back to the allocator and it pushes it onto the front of the free list.
Nice. Where does it store the pointers for this free list? Does that take extra memory?
Ah, that's the clever bit. When a chunk is not being used, i.e. that's on the free list, its memory isn't needed for the actual object data. So the allocator uses the first few bytes of the unused chunk itself to store the next pointer for the free list.
Oh, that's smart. So no extra overhead for the list structure itself.
Exactly. It repurposes the memory of the free blocks. This means pool allocators completely eliminate internal fragmentation for that specific object size, and they make allocation and deallocation incredibly efficient. Perfect for things you create and destroy a lot, like maybe bullets in a game or network packets of a standard size.
Okay, linear for temporary bulk, pool for fixed size high churn. These sound really useful.
Ah,
But I seem to remember hearing that using custom allocators in C++ used to be a real pain, like really difficult to integrate cleanly.
oh, you are absolutely right. Before C++17, it was challenging.
What was the problem?
The issue was often called type contamination. See, back then, the allocator type was part of the container's template parameters. So std.vectorant my allocator was a completely different type in the compiler's eyes than std.vectorant your allocator, or even just the default std.vectorant.
Ah, so you couldn't like pass a vector using my allocator to a function expecting a vector using your allocator, even if they both held integers.
Exactly. You couldn't easily store them in the same collection. You couldn't write generic functions that worked with containers using different custom allocators. It made them powerful in theory, but really cumbersome in practice. Lots of template metaprogramming gymnastics were often needed.
Right, that sounds like a nightmare. So C++17 rode to the rescue.
It absolutely did. C++17 introduced the Polymorphic Memory Resources library, usually just called PMR. It's found in the memory resource header.
Polymorphic Memory Resources. Okay, what does that do?
Its core magic is that it decouples the allocation strategy, like linear or pool, from the containers type, using runtime polymorphism, good old virtual functions. How?
There's an abstract base class called std.pmr.memoryResource. It defines the interface for allocation with virtual functions like doallocate and dodeallocate.
Okay, an abstract interface.
Then you have concrete allocator strategies that derive from memory resource and implement those virtual functions like a linear memory resource or a pool memory resource.
Right.
And finally, there's a special allocator called std.pmr.polymorphic This allocator doesn't implement the strategy itself. Instead, it just holds a pointer to a std.pmr.memory resource. When you ask Polymorphic Allocator to allocate, it just forwards the call to the doallocate virtual function of the memory resource it's pointing to.
Ah, so the container type itself only depends on polymorphic allocator.
Exactly. Now, std.pmr.vectorant, which is just a type alias for std.vectorant, std.pmr.polymorphically is always the same type, regardless of the underlying strategy. You can pass a pointer to a linear memory resource or a pool memory resource to its constructor, and it just works. So you can change the allocation strategy at runtime without changing the container's type.
Yeah.
That solves the type contamination problem.
Completely. It makes using custom allocators so much more practical and flexible. And the standard library even gives you some ready-made resources out of the box.
Oh, yeah? Like what?
There's std.pmr.monotonic buffer resource, which is basically a linear bump allocator. It can even be configured to use a small stack allocated buffer first for super fast small allocations, falling back to the heap only if that overflows.
Wow, stack allocation speed. That's neat.
Yeah. And there are pool resources too, like std.pmr.unsynchronized pool resource and std.pmr.synchronized pool resource. They manage pools for various block sizes, which can be really handy for things like allocating nodes for std.pmr.list or std.pmr.map efficiently.
This is all great stuff, but for someone learning C++, maybe self-taught, seeing all these options at default, linear, pool, PMR, can feel a bit overwhelming. How do we actually decide which one to pick in a real-world project?
That's the million-dollar question, right? It really boils down to understanding the trade-offs and matching the tool to the job. The core principle is this. The more constraints you can accept about your memory usage pattern, the simpler, and therefore faster, your allocator can potentially be.
More constraints equals more speed.
Okay. So let's summarize, maybe. The default std.allocator, using global new delete. It's the most general purpose, no constraints really. But as we discussed, it's often relatively slow due to system calls, potential lock contention in multi-threaded code. It causes fragmentation, and it generally gives you poor data locality. So when to use it? Honestly, it's fine for non-performance critical code or when development speed is way more important than runtime speed. Quick prototypes, maybe?
Okay, the default is convenient but potentially slow and messy.
Then the linear arena allocator, monotonic buffer resource in PMR. Extremely fast, O1 allocation. Perfect spatial locality within its arena, no fragmentation within the arena itself. The constraint, you can only deallocate everything all at once. So it's ideal for temporary, short-lived objects that share a common lifetime. Think data processing for a single request, calculations within one game frame, temporary buffers for parsing a file.
Got it. Fast in, fast out all at once.
Next, the pool allocator, pool resource in PMR. Very fast O1 allocation and O1 deallocation. It completely eliminates fragmentation for objects of its specific fixed size. The constraint only works well for objects of that one size. So this is your go-to solution when you have high churn, lots of creation and destruction of uniform-sized objects. Classic examples are game entities like bullets, particles, nodes in a linked list, or tree if you must use them.
Fixed size, high frequency. Makes sense.
And maybe briefly mention a more general free list allocator. These try to handle variable allocations, often by maintaining multiple pools or using more complex logic to find fitting blocks. They're generally better than the default malloc new if you need more control, maybe better locality or less fragmentation, but they can be slower than pools or arenas, sometimes OM, to find a suitable block. They're kind of a middle ground if your patterns are irregular, but you still want to avoid the raw OS calls.
So it's really about analyzing your memory needs for a specific part of your code.
Exactly. Match the allocator's strengths and constraints to your problem's specific memory usage pattern. Don't just throw a pool allocator at everything.
You mentioned game engines earlier as using these. Can you give us a bit more detail? How does a complex system like a AAA game engine actually put this portfolio of allocators into practice?
Oh yeah, game engines are fantastic examples because they operate under such tight constraints. They're essentially soft real-time systems. They absolutely must hit their frame budget, typically 16.67 milliseconds for 60 frames per second. Any unexpected stall, like from a slow memory allocation or garbage collection pause, which C++ avoids, is unacceptable. It ruins the player experience.
So predictability is key.
Absolutely. So they use a whole portfolio of allocators, usually managed by a central memory manager. The very common one is the frame allocator or scratch allocator.
The linear one we talked about.
Exactly. Usually a linear allocator. At the beginning of each frame, it's ready. All sorts of temporary systems use it, maybe AI pathfinding calculations, physics collision data, generating rendering commands for the GPU. They all allocate rapidly from this frame arena.
And at the end of the frame.
Poof. The allocator just resets its bump pointer. All that memory is instantly available for the next frame. No individual delete calls, super fast cleanup.
Nice. What else?
Then you'll definitely find object pools, lots of them. Specific pools for bullets, maybe another for particle effects, another for small enemy AI objects. When you need a new bullet, you grab one from the bullet pool. When it hits something, you return it to the pool. This gives fast creation destruction and tends to group similar objects together in memory, which is great for cache performance when processing all bullets, for instance.
So specialized pools for common object types.
Right. And then for everything else that doesn't fit neatly into those categories, maybe level loading data, configuration strings, more persistent objects, they'll often replace the system's default malloc and new entirely with their own custom high-performance general-purpose allocator. This might be a sophisticated free list implementation tuned to reduce fragmentation and handle multi-threading efficiently, much better than the generic OS one.
And having this fine-grained control must really help with debugging too, right? I've seen tools like Unreal Engine's Memory Insights.
Absolutely. Because the engine controls all allocations, it can tag every single allocation with metadata. What system allocated it? What type of object is it? How long has it lived? Then tools like Memory Insights can visualize all of this, track down leaks, identify fragmentation patterns, and see exactly where memory is going. It's a level of visibility you just don't get when everything just blindly calls the global new.
Okay, that's games. What about the absolute bleeding edge of low latency, like high-frequency trading? They operate in nanoseconds sometimes. How do they handle memory? Surely they can't afford any hiccups.
HFT is another level entirely. They operate on a razor's edge where latency is everything, measured in nanoseconds, and predictability is paramount. For them, the golden rule is crystal clear. Zero dynamic memory allocation on the critical path.
Zero. Like none at all.
None. During active trading, when processing market data or making order decisions, they simply cannot afford the non-determinism of asking the OS for memory or even traversing complex free lists. The potential latency spike is just too high.
So how do they do anything? Where does the memory come from?
It comes from total pre-allocation. Before the trading day even starts, before the market opens, the HFT system allocates all the memory it could conceivably need for the entire session.
All of it, upfront.
All of it. This means huge arenas for buffering network messages, massive object pools for every conceivable type of order report or market data update, pre-sizing all internal queues and daisy structures. Everything is allocated and often even constructed up front.
So when a market data packet comes in off the network?
They don't new an object to hold it. They grab a pre-allocated, possibly even pre-constructed object from a dedicated free list or pool associated with that data type. That allocation is guaranteed to be a deterministic O1 pointer manipulation. No system calls, no locks, no searching free lists, just grab the next available slot.
Wow. And I bet they're obsessed with cache locality, too.
Obsessed is an understatement. It's an intensely cache-obsessed design. Data structures are often manually laid out in memory to ensure related data items fit perfectly within CPU cache lines. Access patterns are meticulously designed to be sequential whenever possible. Custom allocators, pools, and arenas are the fundamental tools they use to enforce this strict, hardware-sympathetic memory layout.
So in HFT, the memory layout isn't just an implementation detail.
It's as much a part of the algorithm's performance characteristics as the C++ code itself, its fundamental systems design.
Okay, wow. This has been quite the journey. This deep dive has really shown us that just using new and delete without thinking, well, it has hidden costs, system calls, fragmentation, and maybe most critically, the potential to just destroy data locality and kill CPU cache performance.
Absolutely. And hopefully, understanding the why, the memory hierarchy, the cost of cache misses, the importance of spatial locality reveals why these things matter so much. Custom allocators aren't just fancy optimizations. You can think of them as layout engines. They give you the power to dictate a cache-friendly memory design to control how your data interacts with the fastest parts of the CPU.
And the good news is that the C++17 PMR framework makes these advanced techniques much more accessible than they used to be. It lets us pick the right tool, the right allocator for the right job, without getting tangled up in those old type contamination nightmares.
Definitely makes it easier to adopt these strategies, but there's one crucial caveat. The single most important principle in any performance engineering work still applies. Profile first.
Ah, yes. Don't optimize blindly.
Exactly. Custom allocators are powerful tools for solving measurable bottlenecks. Implementing one just because you think it might be faster without actual data from a profiler showing that default allocation is a problem is premature optimization. And honestly, a poorly implemented custom allocator can actually perform worse than the highly tuned default allocator that comes with your compiler and OS. So measure, identify the bottleneck, then apply the appropriate fix.
That's excellent advice. Ultimately, mastering C++ allocators seems like it's about moving beyond just telling the computer what to do and really digging into how the computer is likely to do it under the hood. It's about engineering truly exceptional software that works with the hardware, not against it.
Well said. It's about understanding the machine.
So, for everyone listening, we're curious. What memory challenges have you run into in your own C++ projects? Did any of this sound familiar? And maybe after this discussion, what's one area in your code you're now curious to profile to see if maybe a different allocation strategy can make a difference? Let us know in the comments below.